All right. Is it working? Yeah, it looks like it's working. Okay.
All right, everybody. Welcome to the last lesson day of the semester. Hard to believe. Oh, not semester, quarter. You know what I mean? Yeah, hard to believe that we're already in that far in. Anyway, today we'll be doing some review for circuits. That will be ending off with some review problems that will give you guys some good practice for the exam next week. There'll be some on there that you won't necessarily see on that exam, but you'll see some. Yep.
What next week is it?
Thursday. So Monday will be a free day where you can catch up on work or you can just do whatever. Tuesday is the marine presentation, right?
Tuesday, yeah.
Yeah, Tuesday. And then Wednesday is a proper review day covering all the subjects, and then Thursday is the actual exam. All right, so to start, we're going to look back at our old friend Ohm's law. So the amount of current that moves through a circuit is dependent on how much push there is for the potential difference of the battery source divided by how resistive the material that the circuit is made out of is. So most of the resistance will be covered in devices that are in the circuit that intentionally try to take current from the battery, or they'll just come from the natural resistiveness of the material. If, for example, you're trying to measure your own resistance, if your skin is going to be a lot more resistant. But looking at this equation here, we've got a few relationships we can pick out based off of one varying with the other. So if the voltage goes up and the resistance stays the same, what happens to the current? It's bigger, yep. As you get more voltage and the resistance stays the same, the amount of current will increase. If the voltage remains the same and the resistance increases, what happens to the current?
It goes down.
It goes down. Because there's less push. Well, I mean, there's the same amount of push, but there's more resistance, more bouncing inside of the material, and that lowers the speed of the overall current. What happens if the voltage remains the same, but the current increases? What happens to the resistance?
It goes down.
It has to go down, yep. Because as there's more current for the same amount of push, the overall resistance has to go down to compensate. That's what happens in your parallel circuits. When you add another wire with another resistor on there, the overall resistance will go down because of the fact that more current is being pushed through the overall circuit. So that's a brief look back at Ohm's law in general. Now we'll look more specifically at some of the relationships that you see when you're working with series and parallel. So to start, let's do series. And while I write this up there, if you have a whiteboard, you can draw a simple series circuit on there in order to try and add your own notes and follow along. If you don't have a whiteboard and you see an empty one, go ahead and grab it. Yep. So in a series circuit, we have a certain power supply, we'll call it Vs. And we have, in this particular example, 3 resistors. We'll label them 1, 2, and 3. Each one has a certain resistance. We're not going to worry too much about numbers for this part. So what do we know about the current flow in a series circuit?
All the resistance adds up.
All the resistance does add up. So that's another relationship that was on the but what do we know about the current flow across this circuit?
It's all the same.
It remains constant because there's only one wire. So if you were to draw out here a representation of the current flow, it would be the same here, here, and here. So the way to describe that is current is equal at resistor 1, is equal at resistor 2, and is equal at resistor 3. So the current always remains the same across the series circuit. because there's only one wire, so there's only one way for the current to flow through the entire circuit. And you already mentioned the resistance relationship, so if you want to find what the total resistance of the circuit is, you just add up all the sources of resistance. So the value of resistor 1 plus the value of resistor 2 plus the value of resistor 3. You actually use this number in combination with Vs to find what the current is in the overall circuit. So you have to, if you want to find the current in a series circuit, you take whatever the voltage of the power source is and divide it by the sum of all of the resistances. That way you'll know how much current is flowing through every part of the circuit. Now, here's a question. What's the relationship between the voltage at the source and the voltage used up across each resistor? We can actually find out what it is by just moving this equation around a little bit. If we say V is equal to I and R, well, if we say that the voltage drop at point 1 is equal to the current times the resistance at point 1, well, we already know that resistance has a relationship where you add all the resistors together to get the total resistance. So do you think we can apply the same logic to the voltage across each resistor? We can. So, in actuality, the amount of voltage from the source is equal to the amount of voltage used up across each resistor. Or another way to phrase it is voltage from the source minus voltage used up across the first, minus voltage used across the second and third, equal to 0. Terrible 0.
It has a little pair.
Yeah. So, the way you can look at it is, there's a certain amount of voltage assigned here, a certain amount of voltage assigned here, and a certain amount of voltage assigned here. You can't assign more voltage to each resistor, to all of the resistors, than you have initially applied to the circuit. If you do, then that means that there's another voltage source being applied to the circuit somewhere, which brings up some questions about how your circuit is set up. But that is the overall set of relationships for series circuits. Pretty straightforward, pretty simple. So go ahead and pass your whiteboard to someone else who hasn't used it yet, and they will draw a parallel circuit so that we can talk about those relationships next. Got here a simple parallel circuit. So what relationship do we know already off the bat? So what do we know about the voltage for a parallel circuit? Do you remember how voltage works across a parallel circuit? Yeah.
Wait, how voltage works?
Yes. So if you have this much here going out of this wire, how does it apply to this wire versus this
All the
wire
same.
versus this? All the same. Yep. So the voltage at the source is equal to the voltage being applied to every wire in the parallel circuit. So each one of these is drawing the same amount of potential difference out of the battery at the same time. So depending on what their value for the resistance is, they'll have different currents applied to them. So how do we figure out how much current is coming out of the battery here at the start of the circuit?
Do voltage divided by R 3 times and add them up.
Yep, you add up all of the current sources. So the total amount of current coming out of the battery has to be equal to the amount of current applied here, here, and here. So you just add all of them up. So there will be a whole bunch of current coming out of the battery whenever you add another resistor in parallel. The more of them you add, the more current that has to come out of the battery, because each of them will have the same potential difference applied to each one, and therefore you'll have more and more current being applied to each resistor. Now, the relationship for the resistance of the overall circuit is a little bit of a strange one, so I'm just going to give that one to you. The equivalent resistance, in other words, if you were to take these three and collapse them down to just a single resistor, how you find what the resistance of this is by doing 1 over the value of that resistor is equal to 1 over the value of the first resistor plus 1 over the value of the second resistor plus 1 over the value of the third resistor. This is a bit of a messy equation to be working with when it comes to parallel, but I promise it works. And it's hard to explain why, but just in general, remember back over here, if this goes up and this remains the same, this has to go down. So this is just a way of mathematically showing how much this goes down when you add more resistors and cause this to go up. So that is the set of relationships you have for series and parallel. Most of them are pretty easy to understand. It's just this one's a little tricky. So let's go ahead and just do a very quick work example to show you how it works. We'll say we have one that is 2 ohms, and we have one that is 4 ohms. So what would be the value of the single resistor that would replace these two if we were to find it? So 1 over 1 plus 1/4, which if you double this to 2/4, you can add those two together pretty easily to 3/4. So that is equal to 1 over the resistance we're looking for. There's two ways you can do this. You can just flip them, or you can do this the slightly longer way of 3 times that resistance value is equal to 4. So the equivalent resistance of them would be 4/3 or 1.33 repeating 3 to infinity. So what this means is, even though you've had in the circuit a 2 ohm resistor and a 4 ohm resistor, when you add them together in parallel, the overall resistance drops to be smaller than either of them at 1.3 repeating 3. That's a pretty small, pretty big drop, right? So, now that we have all of these relationships in mind, including the wonky one, that is this one, let's try and apply them to a more complicated setup. So, we've got here a circuit that looks a lot like the one that you guys did for the last part of your lab over the last couple of days. You've got a resistor here that connects to 2 resistors that are parallel to each other, followed by another resistor that ties back into the power source. So the question to start with is, how do we find what the overall current across the entire circuit is? Now, just looking at it like this, there's not really much you can do directly, because if this were series, you could just add all the resistors together, divide them by the power, the amount of voltage, and then you're good. But in this case, we don't necessarily know what the equivalent resistance of this one is. Let me show you how we can do this. So what you can do is you can isolate this part and just analyze it by itself. So if we just look at it as this segment over here, we can make a just sort of equivalent single resistor that works exactly the same way, practically speaking, as far as the current goes. And to do that, we use that relationship for the resistance over there that we just showed. In this case, 4, 4, 1/4 plus 1/4, which is 1/2. And if you flip those, resistance of this hypothetical resistor that would be replacing them would just be 2 ohms. So that's a pretty easy step in order to try and fix the problem of what would this be if it was a single resistor instead. So let's just draw a hypothetical one to replace it. Over there. Now 2 ohms. So if we have this new circuit, let's do that part. That's not very visually descriptive. Let's just draw another. So we have this one here, this big one here that we've made up based on the one, the parallel ones that are there. We got 2, we got 8, we got 10, we've got 20. So now that we have the voltage and the resistances, how do we find what the current is now?
Add them all up. Divide 20 by 20.
Yep. So you just add each of the resistances together and divide that number over 20. Plus 2 is 10. 20 over 20 is equal to just 1. So looking back at our original equation, now C. The current flowing through the whole circuit is just 1 amp. Alright, so we managed to figure what that is. Figure out what that is. So, what is our next step? Well, we want to find what the voltage is across each resistor. Let's do that on the next page.
Just current times resistance.
Yes, so we know what it is now. It is 1 amp. So let's apply that to the first one. So V equals IR. That's what we use in order to figure out what the voltage is across this one and the voltage is across that one. So for the first resistor, it is 1 amp times 8 ohms, which is what? 8 volts. Nice and easy. Do the same thing for the last resistor. 1 amp times 10 ohms is equal to 10 volts. Alright? But how do we figure out what this one is?
We just take the imaginary resistor we made out of them, it's 2 ohms.
Yep. So bringing back the imaginary resistor, which was 2. So the value for the voltage drop across the parallel one is 1 amp times 2 is equal to 2 volts. So if we add those up really quick, we find that 2 plus 8 plus 10 to 20. Does that match what our voltage source was?
Yes.
Yes, it does. All right. So we know that we're working with 2 volts coming through here and here because they are parallel. So the last part of this is we want to find out how much current is going through each of these. So how do we do that? So we have the voltage going across each of those, and we know what their resistance is. So what is the current going across this one and that one? Yeah. I'll give you a hint. The equation for it is way over there.
go. So we want the I going across here and here. We know what the voltage is going across both of them, and we know their resistance. So how do we find what the current is? V divided by R? Okay. So I for number 2, let's say, is 2 volts divided by 4 ohms, which is equal to 0.5 amps. And if we add those together for both of them, since we know that this is exactly the same resistance and everything. If we add those two together, what do we get? Well, 0.5. Get 1, yep. So 2, the current of resistors 2 and 3 added together is 0.5 plus 0.5, which is 1. And that is the amount of current that we know has to flow through the entire circuit. So that proves that these two are indeed correct, and they have the right amount of current flowing through them that has split into 0.5 and 0.5. Now this is a really complicated series of steps in order to try and figure out how to solve a relatively simple complex circuit, but each individual step is stuff that you would do on the exam separate from this big whole setup. So you don't really need to worry about solving something this big complicated, but each useful step that we took in order to get there is something you can end up doing. So, with that in mind, let's pass out some practice problems that you guys can use to get ready for the test. Do you have any questions before you start? Practice. Sure. It is on Thursday. You'll have a review day just before it. No worries there. So this is 10 problems. They're pretty easy. I made sure that there's stuff that you would much more likely see on the exam versus this whole thing that I showed you. You can write your name in any white space you find, but the easiest spot is probably in the far back on the bottom of it. And if you have any questions, please let me know. Why I converted it? So the reason why I converted it, I made an imaginary resistor that has the same resistance value as those two, using that equivalence thing that I did. The reason I wanted to do that is because I wanted to find out what the current is across the whole circuit. And in order to do that, I need to know what the resistance of the whole circuit is.
So you took that and did 1/4 plus 1.
Yes, 1/4 plus 1/4, 2, and then you flip that number to get what the resistance of the imaginary resistor would be. Yeah, then you could find out what the whole current is by adding all the resistance in the circuit. You divide the voltage applied to the circuit by the total resistance that you found by changing those into a single resistor. And from there, the rest is just an application of the relationships that we showed there.
That was the part that was confusing, like why are you doing all this stuff?
Yeah, that step in particular is the tricky part.
Are we gonna have it on our test?
No.
Okay.
That-
I
yeah.
don't like that.
This problem that I just showed you guys is more complicated than anything you're going to have on the actual exam. It's just for the sake of both giving you a whole bunch of examples of isolated, like individual steps you can do, and giving you an idea of how much more complex it could be, but you don't have to work on it. Yeah, that's okay. No.
He's talking to his fans. This one would be a series, right? This is a series, right? It's like-
Yes, those two are in series. So, for example, for that one, if you wanted to try and simplify that to
once you find what the equivalent resistance was of all three of these wires, you add these two together first, and then you do one. That's an example of some complicated stuff.
They were four.
You would add them together first, and then you put one.
Okay.
So it actually.
Oh, I was like,
Yep.
thanks for your opinion, but no.
Thank you. That's my solar telescope. The physical science classes we're using it today.
Yes, you have a question?
Okay. All right.
Thanks.
I'm glad everybody enjoyed it. Anybody get good pictures?
Which part
Be serious. It's hard to do.
Somebody was able to get a good enough picture where they actually have the sunspots in their vicinity.
That's nice. I forgot to pass out this graduating fuse class.
Last year.
Darn it.
Yeah, I remember.
Forgot to pass it out.
So,
Would you like me to pass out a blank paper for you to work with, or you already been taking
they
that?
don't come early, whatever.
And or if I'm not here, I mean, I'm gonna leave this room. We can go with that. So feel free to just come in and grab it. Yeah. Yeah, I'll come in. And then I'll go, yeah. Okay, great. You're welcome.
Well, actually, flip that one so that it's 10 divided by 12.5, but otherwise you're right. Yep, and that will give you what your current is for that.
Oh, shit, I brought my solar telescope in and for a physical science class went out and observed sunspots today. So, yeah, we were just talking about how that went.
Interesting.
Yeah.
Yes. You do add them, yeah. What you do is you add those two, that gives you what the total blockage basically is in the circuit. You divide the power source, the voltage, the 10 volts, by the total resistance. 10 by 12.5, yep. For which one?
So I can find the terminal current, so we don't know what the resistors are, right?
Resistance.
But are they all the same because it's parallel?
Oh, in that case, you already have the currents, so you just, add them all together.
Okay, so ohms is the current.
Amps is the current.
Yes. Oh,
Ohms
these
is
are
for
amps.
resistance, yes.
Okay. Oh, and then these are ohms.
Those are ohms. And the A refers to current.
Okay, that makes sense. Thank you.
10 divided by 12.5, I believe that's 0.8. So, 10 divided by 12.5. Yep, 0.8. I'm not sure.
So do you add the total resistance, or is it just the same for each? So when I put, like, so is the resistance is it one?
Yes, it is 1.
So would I add it, them all together, or would it just
Oh, that
be
would,
one?
one is the value for the total circuit.
Okay,
Yes, so, all it's asking you for is that one.
and it's one because it's a series, I mean, a parallel.
Yep,
But
parallel.
if it was like series, like let's say this one right here, would you add it?
It's basically working off of the previous problem where you added up to find what the total current is.
Right.
Now that you know the total current, you can just figure out what the resistance of all three circuits would be added together.
Yeah, okay, that makes sense.
Yeah, individually, you do V equals IR for each one. So you have the 0.8 as the I, and then you times that by each individual resistor's value of 5, 5, and 2. So you do 3 calculations. So say if you label this as 1, V1 would be equal to this times that, V2 would be equal to this times that, and so on. Don't forget, 0.8. So it would actually just be 4. Yep. It's because it's 0.8.
If it was 8, then it would be 40. Yes, that's what the equation is.
And then I would just,
It would be 4. So what you're doing is you're doing 0.8 times 5.
oh.
Yeah. I probably should have left it as a whole, as a decimal, but that would make the number really big. So, if you wanted to find what the total voltage is, yes. That's what the next problem is. Oh, no, it's across each resistor, so you do an individual calculation.
Oh, okay. How is that with the next one?
It has different numbers, but it's the same principle for the problem, so you just add each one up.
So I'm gonna do.
Oh, no, for 5 is a different problem. 5, you just add each voltage together.
Okay. And then just add this.
Yeah, you could add this one times 10, but yes. Actually, should have clear those my directions.
So.
What happens when you write them in less than 10 minutes? I wrote it in less than 10 minutes because that's how much it would come up with. No, I meant, I wrote these in less than 10 minutes. That's how long it took. Doing good?
I think you were just subtracting from it. It's like, it's about like, it's taking away two.
How you doing?
I think that's. Did anyone else finish?
In this case, 10 divided by 12 is 5. I believe is 0.8. But you have the right answer.
I swear. Oh my goodness. And my calculator. I did the same thing.
Yeah, it can throw you off if there's just one small thing wrong. Anyway, so for the next one, you see that V equals II over there? You just use that for each individual resistor, and then you can use that to find how much voltage goes through each resistor. So in this case, the 0.8 amps, that is your current across the whole circuit. And then you multiply that number by 5 for the first voltage drop, then 5 again for the second voltage drop, and 2 for the last voltage drop. So 0.8 times 5. Let's see. Oh, well, you just add them up, but that's fine.
Yeah.
This is right there. Yep. And yep.
Do I add them up?
No, you just do them separately.
Then that's my answer.
So 1 is 4, 1 is 4, 1 is 2. Yep.
Okay. Then it's actually 25 total voltage.
Yep. You're already given the voltage across each one. So just look up there. See how VS is equal to 1, 2, and 3. Just add them together.
Just add them.
Yep, just add them up. 5 plus 7 plus 12.
Mr. James?
Yes. Sure. Series. So 10 plus 2, 2.5 is 10 is 1.5. So 10 divided by 12.5. Yeah, what you did is 12.5 divided by 10.
Oh,
Yeah.
right,
Yep,
okay.
it's fine. So those are right. Those are right. Here's the thing. Here's a question.
Okay.
How much voltage does each wire across these parallel take? You have them in parallel.
12.
Yes, each one is 12.
Okay.
Because in this case, the resistance numbers are right here. It's just the case of each wire is going to take 12 volts.
Okay, wait, so if it's across each, it's 12 no matter what?
Yes, it's 12 no matter what.
basically happening is you have one wire. Each one of them is attached directly to the original battery, and so each one takes the same amount of voltage through each wire. Each one is a possible path for the charge to move through. So the charge moves through here, but it also moves through here, and it also moves through there.
So in a parallel circuit, do resistors just not do anything?
No, they do. They still take the charge. What they do is they make it so, like if one of these was a blank wire, then you'd go back to the old problem that we had in the simulator of you attach a blank wire to a battery, the battery's gonna catch on fire.
Right.
It'll still carry the same amount of voltage through, but because there's no resistance here, the current is going to skyrocket.
Okay.
Yep.
That makes more sense. Thank you.
Yep. Yes. What is the total resistance? Well, in this case, you have what the voltage is, and you have the total current, which is 12.
Oh, so we have to, that's why.
Yep. Yeah, you're finding what the total resistance of all three parallel would be if they were added together. So in this case, you would just use R is equal to 100 going V over I.
Wait, so voltage doesn't change.
R is equal to V over I. What that equation is doing is it's swapping the place of the current and the resistance, but it's otherwise equivalent. So in this case, since you know what the V is and you know what I is, you just divide the two.
It's like for 7, is this right?
Yep.
Okay, so the voltage doesn't change, but the current does?
Yes, each resistor will draw a different, well, it will have a different resulting current. Because even if they're drawing the same voltage, because each resistor has a different value, they'll cause a different current to flow through them.
Okay.
So like each wire has a different amount of like permissiveness, that the amount of electrons that are flowing through it can push through.
Yeah.
If you've got a thin wire with a relatively little resistor, you'll have more current. And then if you have a thicker wire that has a heavier resistor in it, the current will slow down because there's still that blockage.
Right.
You have the same push, but the amount of pull back is going to increase the lower amount of current.
Okay, so then for this one, is it 12 because it's just the current that's going through?
You're just adding all the currents together. If you've got that current flowing through one wire, and that current flowing through another wire, and that current flowing through the last wire, all of them must add up to how much current is flowing through the whole wire as a whole. I will give you them back on Monday, after I've graded them. Yes. Sure. No, you've already found what the voltage is, so that's basically how powerful, you don't need a multiplier. What you've done is you've added the voltage across each resistor, so that's how much of the resistance, how much of the voltage from the original power supply is being applied to that resistor. You use V equals IR when you know what the current is passing through a resistor, and you know what the value of that resistor is. Because you want to find how much voltage is being used up at that particular resistor. In that case, actually, that was a trick question. So, no, it's okay. It's okay. It's a very simple question. Going back to that example I drew up there, we've got 3 wires all attached to the same battery. What do you think each one pulls the same amount of voltage? And that's what's happening with the parallel. Each one is drawing the same voltage from the battery. Yep, as well. Yep. It's this one that is actually has a difference between them. So that one, using the original Ohm's law, I is V over R.
this way, and the current flow this way. We're all connected. So all of them, when they get to this point, I think past where all of them were split, they have to come back together, their total currents have to come back together to go back into the battery.
Current in the circuit.
So what you do is you just add each of their individual currents.
Yeah.
So that's how much current is the whole, circuit.
12 is gonna split into 2 and 10, and then 4, and then that 10 splits into 4. So it's
Just that.
total resistance. Total resistance means overall resistance of the circuit, which is a measure of, it's like if you replace a bunch of resistors with one single resistor, right? To get the same current, exactly, yeah, to get the same current coming out of the battery, yes, 12 volts.
If you added them together, then it's basically this.
Oh,
relationship of
yeah, that's 12 amps.
the total current is equal to
And then
the sum of all the
resistance of the circuit. Did he add? Did he tell you to add something?
I remember.
Oh, you just did the, you did the calculation of both the arrows. I see.
Is this step over here,
Yeah.
where you make a sort of imaginary resistor that has the same value as the bulk. In order to find out what that is, you're taking these two, you're turning them pretendingly into this one. So you use 1 over both of those resistors, add those together,
Is this all we're doing today?
and then you flip them.
Yes.
We have more.
Yes.
Are you collecting
5
these
plus
papers?
5.
I got that question.
Yes.
Oh, 2 or 5. And now that you have that, you know that it is the inverse. So basically what you do is you flip both of them. You flip the one over RP, so it's RP. And you flip the 2/5 to 5 over 2. Yes.
Yes, you are. Yes, you are. Yes, you are. Oh my gosh. Oh, just so we're not. Okay.
I can't have students in the class.
In this case, yeah, it's 12 amps. Well, thankfully, that's the point where the whole current is. Like, when you added these three together to find what the total current was, that's that number. No, in this case, you're just looking for what the total resistance of all three of these is. So, you look at I equals V over R, and then you swap the R and the I. Yes. Yep. It's 12 divided by 12. So the total resistance, or what the value of the resistance is when you consider all three of these together, is just 1. That's one of the answers of what the resistors could be. I just let them blank because there's a lot of values that could add up to 1. Sure. Yep. These are magnitude higher than they should be, but that's fine because I'm not sure you know what's happening. So that's fine. I know what you meant, and you got the right answer anyway, so. 4, 12.
I'm watching you as a
Yep, you're good. If you guys finish early, then I guess you can work on your lab scripts from both last week and this week, or you can finish your homework if you haven't done that already. But if you need any help, let me know. Yep, got those right, got that right.
Yeah.
So, do you know the trick for this one? So looking at the relationships for parallel, we have it so that the voltage So,
What's your
actually,
dream job?
it's
Oh,
just
wait, you
12
wanted
for
to be
each
an
position.
aerospace engineer?
Okay.
Yep.
That's all.
Yep, that was just a trick question of, do you remember what the relationship is for those?
Oh, how many kids you want to?
Alright. So for this one, you use I equals B over R across each wire. So.
Oh, that's so dark.
2, 12, 4, 12.
Oh, you're right. I'll do that. Instead of one. Instead of -1. Okay. Okay, kids, and then.
12 over 8 would be 4/3 basically. Or, no, 3/2. That's my math wrong.
What is it?
It would be 3/2. That's my math wrong. I was thinking of dividing by 3 instead of 4 for some reason. Alright.
You just add them up.
Yes, you add the total current. So well, for that one.
Wait.
For this one, you've found what the currents are for each one. So like, the current across this wire is that number. The current across this wire is that number. The current across this wire is that number.
I'm not gonna do 3 each every.
Yep. And so for the next one, you just add all of the currents together to figure out how much current is coming out of the battery.
I've added it.
Looking at that diagram up there, what you're basically doing is you're saying that current from that wire, that current from that wire, and that current from that wire all have to add together to what the current is going back into the battery. So that's why you add.
I'm joking.
How you doing?
Good.
Anything else for your answers? Need help with your answers? So, with these two that are circled, you see those are gray. How about these two that are circled? Yes. Alright, so for this one, how you find the current is first you add these two together to find what the whole resistance is across the circuit.
Oh wait, no, it's
And then you divide this number by these two added together to find how much current is flowing across the entire circuit.
Oh my god. Oh shit.
Alright, how many minutes left? Let's see. 1:04, so that's like 5 minutes left. Alright, 5 minutes left, everybody. If you're already done, if you have your name on there, feel free to push it to the side so I can collect it. And the rest of the time is yours. On Monday, we will be having a free day, so if you are behind on anything, you can work on it then.
You're happy? That's good.
What are you guys drawing?
We're playing a game. 1, 2, 3, 4, 5. Yes!
I'm not familiar with this game.
I can eat 1, 2, 3. Hold on. 1, 2, 3, 4, 5. You're not these. 1, 2, 3, 4, 5.
You both have your names on here? Yes, you do.
Oh, you're right. That's my wife.
Did you have your names on these two?
Yeah.
Okay. Yeah. So I think this is yours, yeah. So your name right there, yep.
Yes.
last two.
Well, I'm looking at it here and it's parallel. It's the bottom one, right?
Dude, these games are.
Yeah, well, actually, in this case, since you've already got the total current right here, you could just divide this by this to get what the resistance is of all three of these, what it's equivalent to. So you do take the equation of V over R, and then you swap these two. So that is R V over I. That's 12. That one, don't worry about, because that one's not actually gonna be on the final.
So the whole thing just one.
Yeah, the equivalent resistance. Also, part of here, if you want to retake that thing we did from last week, and we can work on it on like Monday, I'm pretty sure, you'll be able to finish that. So, real quick to explain for this one, what you do is, you do that thing I did up there, you make an imaginary circuit, which has an equivalent value to them.
So I
Use
did not
that
put in
equation
any
over
grades,
here
'cause you
of
came into this class
the
after the
equivalence
start
of
the
that
semester, right?
whole
So
thing.
basically started grading it right there.
It's a whole thing, but it's not gonna be on your exam, so you don't have
First
to worry about
half of the
it.
score was pretty
So
low.
aside from that, I'm pretty sure you got the rest of them right, so you're all good.
Week 26 homework.
Y'all look at yours?
26 homework, was 8 points.
There you go.
Yeah. For based on. You can hold it back, so. Yeah, so, alright, so you got 4 out of 10 on your method? Let's see, these ones in the red don't count for anything, so don't worry about it. And then you got 7.
You got your name on here?
Most recent. This is, all this stuff is past the label deadline, but since you guys, since you guys, it's twice later, I will let you redo that lab report right there. Look and see what my comments are, if you got a grade like that, if you go on campus and find, you know, and find what you submitted, I made comments that tell you how to improve it, okay? So anyway, so you can go back and you can resubmit that, have a good weekend, one time, I will read this.
Everybody.
Okay, and you can work on the whole program, and that will bring your grade up a little bit higher, okay?